Hi everybody, welcome back to my channel on theoretical physics and sometimes mathematics. Today I want to continue with lesson 4 in group theory and physics. And I've been busy making a lot of latex notes, but I haven't been making many videos, so I have a lot to catch up on here. Today we're going to start with, so this is group theory and physics. Version 2, and this is lesson 4, and today we're going to talk about cosets, conjugacy classes, and group representations. And I'm going to be very general today, sort of like just covering a little bit of abstract algebra. And in the upcoming lessons, I'll give more examples. So don't be too frustrated if I don't give any concrete examples today. It's mostly definitions and just some ideas. So last time when we did Young diagrams, when I introduced them, I talked about partitions. And today, I'd like to start by defining several ways of partitioning the elements of a finite group. Everything I do for a while now will just be finite groups. Eventually we'll get into the infinite Lie groups, but for now we're just doing the finite groups. And so traditionally the first way is we discuss cosets. And so if we have a finite group G and a subgroup H of G, obviously if G is finite then H is finite, then we may form the left cosets, and everything I say, the right cosets are in a complete analogy. And by the way, if you've had abstract algebra, a course in abstract algebra, all of this will be very boring for you, but I'm going to assume that there are some physics students who might not have had a course in abstract algebra, so they may not have seen this. So the left cosets, and we define them by if we have G an element of G, we define GH as the set of all elements GH such that H is an element of H. So basically we take an element of the group and we multiply it by the subgroup. So for instance, if H is equal to, let's say, the set H1, comma H2, comma dot 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 HM, and let's say G is G1, comma, G2, comma, dot, 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 Gn. And usually, we won't need it, but usually like the first element, like H1, would be equal to the identity element of the group H, which is the same as G1, which is equal to E. But we'll find we won't really need that. So for instance, the most trivial, let's first take an element of G. I didn't say G couldn't be in H. Let's say we take an element in H. Let's say we take the trivial element, the identity element. So EH is going to be the set of all EH such that H is an H, which is of course equal to the set of all H such that H is an H, which is equal to the subgroup H. So EH is just the subgroup H. Now let's say we take another element like HI in H unequal to E. So here I'm assuming we have a non-trivial subgroup H. It's not just the identity. Then the question is, what would be H1H? And my claim is H1H, or HI, HI, H equal to H. Why? Because H is a subgroup. And the definition of a subgroup is when you multiply two elements of the group. So, HI, H1, HI, H2, dot, 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 HI, HM. They're all in H. And it's just a reordering. It's pretty easy to see. If we have an element HM, let's say we have an element HM and we want to know HI times what maps into HM, well, the solution is this is equal to HI inverse HM. And again, because H is a subgroup, HI inverse is in the subgroup, and multiplying it by HM is in the subgroup. So we just get a reordering of the group. Now, if we take an element G in G, but not in H, then we don't get a we don't get a subgroup. It's possible you could get a subgroup, but we get a set. With M distinct elements. And this is easy to see because if let's say we take G times HI, and if that were equal to G times HJ, okay, then we could cancel and we get HI. This implies HI equal to HJ. So this mapping on H is going to be 1-to-1, and it's going to be onto, and we get the same number of elements. So this gives an easy proof of Lagrange's theorem, which was stated earlier. Damn it. Early in the course. that the number of elements of a subgroup divides we also call this order, divides the order of the group. And so to prove this, again, we have G is equal to, G1 up to Gn, and H, the subgroup, is equal to H1 up to Hm. And basically what we do is we take an element of G, not in H, let's say GI, and form GIH. Okay. Now the claim is GIH has M elements and is distinct, all the elements, from H. And so to see this, if GI times, let's say, HJ is in H, this would imply that GI HJ equal to HK, which implies GI equal to HJ inverse HK, which is in H. But that contradicts GI not in H. So when we take an element outside of H, we get another M element. So now we have H, and then we have like GIH. And if that doesn't exhaust the group, we take another element, let's call it GJ, that's not in H and not in GIH, and form GJH. Then by similar reasoning, it follows that GJH is distinct from H, GIH. Okay, and now we have M plus M plus M equals 3M elements. So we continue this process until there are no more group elements. in the prior cosets. And so we end up with n, which is equal to the order of G, is going to be equal to the order of H, this is M, times some integer, let's call it I. This is not the identity. And I will be called, sometimes they use this notation. It's referred to as the index of H in G. Anyway, this is a quick, short proof that you can fill out the details of Lagrange's theorem. So that's one way of partitioning a set. Now, an invariant subgroup and the abstract algebra terminology. This is more of a physics terminology that you might sometimes see as normal subgroup. Now this is where the left and right cosets are equal. So we have GH is equal to HG. Now notice what this means here. H is a set. It doesn't mean every element of G. It doesn't mean that. It just means that there exists for all H in H, there exists an H1, let's call it, so that GH equal to H1G. Anyway, as sets, they're equal. And this is also sometimes written as GH, G inverse, is equal to H. So you could think of this as the set of all GH, G inverse, such that H is an H. And this is equal to H. So this is what's called a normal subgroup. And when you have this invariant normal subgroup, we can form a new group called the factor group. And usually we would write it as G/H, and that's sort of what it is. It's a division operation. And this is equal to the set of all cosets. Remember, left cosets are now equal to right cosets, so I don't have to really care which one I use, such that G is in G. And we define the group multiplication group. The group multiplication law by G1H, that's one coset. The operation will denoted by a star. This is equal to G1, G2, H. I'll put a box around this equation. Now, when you look at an equation like this, the first thing you have to say is this well defined? Because every coset usually has many representatives. And it's not instantly clear that the above definition is independent of the coset representatives. Okay, but it actually is. But if H is invariant / normal, it is. And I won't prove that to you here. It's a simple calculation. You can go ahead and do it. And it's pretty easy to see that these elements, these G/H elements over here, form a group. The identity element is just EH, which is equal to H. And then the inverse of GH, so GH inverse is just G inverse H. You can verify that. And associativity follows or inherits from the group G. Okay, so these are factor groups, and I'm not going to go into the whole homomorphisms, kernel, first isomorphism theorem, and so on. You can read about that in any abstract algebra book. A group G is simple if it has no non-trivial. Remember, the trivial subgroups are always the group itself and the identity element. So basically, this is a very important thing. It doesn't say that a simple group has no subgroups. It does have subgroups. Most simple groups have subgroups, but it doesn't have a normal subgroup or an invariant subgroup. So you can't factor it. The alternating group AN, which is the set of group of even permutations on n objects, is simple for n greater than or equal to 5. And I mentioned this because this is related. This is directly related to equations of fifth degree or higher not being solvable. I know I spelled that wrong. By radicals. And if you're interested in this, study Galois theory. Which is important for all of higher mathematics anyway. So if you're into higher mathematics, you'll study Galois theory anyway for details. Now, the classification of all finite simple groups is a major accomplishment of modern mathematics. And was completed in the late 20th century, I think about 1980. It's an extremely long proof. I mean, no one person did it. If you try to read the whole thing, I think it's like 14,000 pages if you took all the articles. And I did, hold on one second. I did ask ChatGPT, so I'm not 100% sure this is right. I think it's right, but I asked ChatGPT for a list of all finite simple groups. And it gave me the following. 1 cyclic groups of prime order. That's obvious. 2 alternating groups, n greater than or equal to 5. And then 3, it says the Lie type groups. I'm not sure exactly what it means by that. Like classical groups, which we'll study in this course at some times, and the exceptional groups. And also, and I'm not familiar with these, twisted groups. I've heard that terminology, but I haven't studied it myself. And then there's these like 26 sporadic groups. You may have read about, like including the monster group. So I think that this is the basic classification, but again, this is ChatGPT, and we know that it's not that good at mathematics. It's getting there, but it's not that good. Okay, so now I want to go into something that's a little bit more relevant for physics. Let's define conjugacy classes. And now, 2 elements in a group G, let's say G1, comma G2, are said to be conjugate. G1 equals H, G2, H inverse for some element H in the group. Now, I don't want you to confuse this with cosets, so I'm going to change my notation here a little bit. Call it G inverse. So we're not concerned here with subgroups, but we're just saying if two elements have this relationship, they're conjugate, then we can form a conjugacy class, and we usually denote it with brackets G. This is equal to the set of all, let's call it G1. G1 equal to the set of all G, G1, G inverse with G and G. So this turns out this is also a partition of the group G into classes, and it will be particularly important for when we discuss group representations. And we saw an example last lesson. You can go back and look at the notes for the group, permutation group S4, permutation group on 4 objects. So we found that there are 5 classes, and for the permutation group, for classes are determined by cycle structure. So if we make like a chart, we had like class and a typical element, and the number of elements. So like first one we would have is like the identity, just the identity element. I'm sorry, that should be the class of the identity permutation, and this would be like it only has one element, but the cycle structure is like 1, 2, 3, 4, and we denote this by E or I. There's only one element. The identity element is always, as you can see from the definition of conjugate elements, the identity element commutes with every other element, so there's only one element in its class. And then there was like a class consisting of 2 1 cycles and a transposition. A typical element was like 1, 2, 3, 4, and we often denote these, we leave out the 1 cycle, so this would just be 3, 4, and there were 6 of those. And then we had a 3 cycle. And a typical element would be like 1, 2, 3, 4, which we denoted just by 2, 3, 4. This had 8 elements. And then we could have 2 transpositions. There were 3 elements of those. And then we could have a 4 cycle. There were 6 elements of those. If you add it up, you get 24 elements, which is equal to 4 factorial, which is the order of S4. So that worked out. Okay. Just as an aside, we will show that the number of irreducible, I'm going to abbreviate irreducible by IRR and representation by REPS, of a finite group, and I'm going to define these terms later, is equal to the number of classes. So for example, we have 1, 2, 3, 4, 5 classes of S4. There'll be 5 irreducible representations. Now let's get to group representation. So we have a group G, and a group representation is a mapping of the group elements into a set of matrices. Of the same size. They're actually all square of the same size, and actually they're also invertible. And but it has to obey, these matrices have to obey, and I'll show this below, the group multiplication law. So so more technically, or mathematically, okay, a group representation, it is a homomorphism of the group into complex. We're always working with the field of complex numbers in physics, so I mean, I guess it could be any field, but complex vector space. So we have phi, which is the homomorphism. It maps G, the group G, into the general linear. So GL, general linear group of transformations on the vector space V. And we have, so what we have is if G maps into a representation, let's call it D of G, then G1, G2 equal G3 in the finite group G. This implies that the product of the matrices DG1, GG2 equal DG3. So that's what we mean by a group representation. Now, a faithful representation maps, what's the terminology? Maps 1-to-1. Actually, Jean Carroll says it should be 2-to-2. But anyway, so if G1 is unequal to G2, that implies DG1 is unequal to DG2. A non-faithful doesn't obey this condition. And there are cases like there are important spinor representations, which we'll cover, which map 2-to-1 onto the rotation group. So like SU2 would map into SO3, but it's a double cover, it's not faithful. Okay. Now, next thing we have to talk about is equivalent representations. So if we have D of G and D prime of G, these are equivalent. Equivalent reps of a group. We're always using the same group if and only if there exists an S such that S inverse DG S is equal to D prime G for all G and G. I think many of you are familiar with this from linear algebra. So those are equivalent reps. Now, all finite groups have an infinite number of finite reps. For example, I can always map the group element into the identity matrix. The identity matrix on like m dimensions. So, G goes to 1 is a representation. So all G goes to 1 is a representation. All G goes to 1, 0, 0, 1 is a two-dimensional representation. These are all trivial reps. All G goes to 1, 3. So we can always get any dimension. Okay, but these are what we call reducible representation. that's not really what we're interested in. So an irreducible representation, which I'll call IRR from now on, is where the associated vector space cannot be decomposed into two invariant, should say two or more. Obviously, if you can do more, you can do two subspaces. So what this means is that the matrices they cannot be block diagonalized. So if for all G and G, we would have like D of G would have the form, this is like a three-dimensional representation. These are all just complex numbers, except where I have the zeros. Then this is reducible, because you have like this block here won't interact when you multiply them with this block. So this is reducible, and it is a direct, and I won't give the exact terminology definition here, but it's a direct sum of a two-dimensional rep and a 1D rep. So all groups, all finite groups, have only a finite number of irreducible representations, which also is equal to the number of classes of the group. And there is a deeper theorem that that n is equal to d1 squared plus d2 squared plus dot 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 dp squared, where n is the number of group elements of G, okay, or the order of G, and the irreducible reps have dimensions d1, d2, comma, dot, 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 dp. And these integers can be equal. This helps a lot when for low order groups. This result, which we'll derive later, is especially helpful, since, for example, let's say like for S3, which has 6 elements, you can see that the only solution to the equation is 6 equal 1 squared plus 1 squared plus 2 squared. So right away you know that there are two one-dimensional representations. These are inequivalent. But irreducible. And there's one two-dimensional irreducible rep. So that's a very useful theorem. And we'll also find that for abelian groups, all irreducible reps are one-dimensional. And this should come as no surprise, because if we have an abelian group, there's like there's no need for matrices. You know, we need matrices, for non-commutativity. But if we don't have, if we have an abelian group and the group elements commute, we don't need matrices. So next lesson, I will give detailed examples. And I'll further define things like regular representations and direct product reps. So that's all I have for today. Thank you for watching. And as I said, I'll try and be more diligent in putting these lessons together and getting to more applications, like on small oscillations and vibrations and symmetries, and then moving on to continuous Lie groups. Thank you very much for watching. Bye-bye.